Okay, let's get started. So welcome to CSE355. I'm your host, Ryan Dougherty. We're going to meet here, as you can see, Monday, Wednesday, Friday, 5:25, 7:30. And then directly after that, we're going to have office hour, which I consider more of a problem session. So if you have something that you're confused about during lecture and you want to discuss a little further, we have like a group problem solving session, which was really helpful the last time I taught it and will hopefully be very useful here. Our TA is Dylan Lucy. He TA'd for me before and has been a TA at this class many times before. He's very intelligent in this material, so use his knowledge if you can. He's going to also do the recitations. So the way recitations work this semester is that they're going to be entirely online. So Dylan's going to make a YouTube video talking about some problems that are related to the lecture material, and as well, during the video, he's going to assign several problems that you will turn in on Blackboard. And the dates I'll show you in a second, if you haven't visited the site yet. I'll talk about the course in a bit when we start getting into the material. So administrative stuff, what we found is that many students just blow off the homeworks, even though they're extremely valuable. So what we have this semester is I've given you two different options. One option is you do the course normally with homeworks, quizzes, and all that stuff with exams, of course. And a second option where you just do exams. You don't have to do any of the other work. There's no grade deduction of any kind. I'm going to treat everyone exactly the same in either option. So on the course webpage, there's a Google form that you need to finish by the second lecture. If you don't, I'm going to put in an option for you, and you may not like that option. So make sure to fill out that form. And then in a few days, I'll transfer it all to Blackboard, and then we'll be all set and ready to go. Any questions on those two options? Or, yeah.
So typically the level of exam for both will be the same?
Yeah, it's just that the option B ones will be scaled up. It'll be the same, but just scaled up points. Other questions?
I have a question.
Yeah.
Will we still have access to the solutions for the?
Yes, you'll have access to everything. You just won't be able to get points for it.
Okay.
Yeah. So, and in fact, there's no way for me to be able to do that. So you have to be able to have access to them. So, other questions? Okay. So email policy. This wasn't really a problem before, but I just want to make sure that we're following this. If you follow this policy, if you have a question about a particular thing, look here, look in the right column, and then you know what to do. Either put it on Piazza, but if it's more of an individual or grading question, talk to me or Dylan, depending on which of the options it is. Grade appeals, it's basically just follow what's on here and everything will be good. And if you have any kind of disability with DRC, please let me know as soon as possible so I can make the appropriate arrangements. It wasn't a problem before, but I don't want it to be a problem. And then now my favorite section. So this class is ripe with cheating of all kinds. And in fact, the two academic integrity violations there are from when I taught this course last, from someone just copying off of for homework. So let me be clear. You can work with other people in terms of formulating a general idea for a solution. In fact, I encourage you to do that. Please talk with each other because this material is difficult. So please talk with your friends about general solutions. But once you come to write down your solution to turn it into Blackboard, should you do that individually or as a group? Individually, please, yes. So writing up solutions individually, there's no issue with that. And there's no issue with citing any material that you use fully and completely. There's no issue with that. But what I don't allow is for you to verbatim copy, like, okay, here's the entire Wikipedia article on Turing machines. The answer's somewhere in there, right? Yeah, don't do that. In fact, that's actually one of the academic integrity violations. Someone did almost exactly that. So, but if you paraphrase it in your own words and cite it, that is completely okay with me. But I don't think I really need to talk about most of these. Penalties is pretty straightforward. Cite your sources, that's what I just said. And use your own words, also what I just said. Any questions about integrity? Okay, yeah. If you think that you're like close to the line of going over the line, there's no harm or foul to ask me. Even if you cross the line before you turn in a homework, if you tell me before then there's no penalty at all. If I catch you afterward and it's really easy to do so, then all this will happen. So, yeah.
So let's say you like have
Mm-hmm.
that like
I guarantee you not a single problem has appeared on the internet ever before. I know this material enough, so I guarantee you that. But if you just happen to find one, then you need to still write it in your own words and say, I got this idea from that source. There's no issue with that whatsoever. Other questions about integrity? Okay. And then just a couple of last minute things. Be professional. Be ethical. You probably should have taken computing ethics right now, so you should know that. Title IX is pretty much as straightforward here, but if you have any issues with harassment or anything like that, I provided a link here. And you're absolutely welcome to talk to me, and I can forward you to the appropriate people for that. And then university policies, don't be a dick. So, yeah. Any questions about the syllabus? Yeah.
Question about how do we get in this building to this lot?
Yeah. We had this exact problem last year. I will contact the appropriate person.
Okay.
So it should be open because there's a class in here to the public. But I believe your ASU Sun card should get you in, but it's ASU, you don't know, that sort of thing. But if you send me an email, I can contact the appropriate people. Other questions about syllabus stuff? Yeah.
How much the grades is said?
You mean like how number grades are translated to letter grades? So generally speaking, 50 points corresponds to a third of a letter grade. So 950 and up is an A+, 900 is an A, and so on. But we've found that this course is really difficult, and that's kind of a high standard. So, but it depends on the course distribution, and it varies from semester to semester. But that's the general structure. So 950 and up is an A+, 900 is an A, 850 is an A-, 800 is a B+, and all the way down. Any questions else about syllabus stuff? Okay, so who's visited this site before? Okay, so if you haven't, I linked to this on the Blackboard page. Please visit this page because this is where everything other than like where you submit stuff will be posted. So the syllabus is there. Schedule is when I made a long list of when things come out and which things are due on which days. And so it'll be really easy for you to keep progress as to how the course is going because this course goes fast. And then I have an announcements page where I will make periodic announcements, most likely daily announcements about like if there's an update to the problem set or if there's a date change to anything. So make sure to check this announcement page. There will be no announcements via Blackboard to your email. It'll only be on this page. All right, and then here's my link and email as well as Dylan's email. And then basically the rest of this page is where links will appear, where PDFs will appear at these links. And where these grade distribution things are, what we think would be really helpful for students to manage to track their progress is to look at a grade distribution and see where they fall in on the list. And then you can make a deciding factor of how you're doing in the class. So for every single graded item in the class, there will be a sorted list of numbers so you can keep track of that sort of thing. Yeah?
What's the default option
Uh, the one that makes my life easiest, which is option B. So if you don't want option B, what should you do? Fill out the form. Okay, so hopefully that's clear. And then problem set 1 is already posted. So when should you start working on this problem set? On July 3rd? When should you work on it? Tonight, yes. Thank you. And does that same policy apply to the other problem sets? Yes, thank you. So I hope you do that. Down at the very bottom, I have the playlist link of lecture videos of so I'm recording these. So there's no guarantee that the recordings will work, but if they do, the videos will appear at that YouTube playlist link. So you can go back if you don't think something is not very clear, or you missed a day and then you need to see what happened, etc. And then the bottom links are for the lecture PDFs. So I'm going off of my own notes because, well, there's a Piazza answer to this, but the default book for this class, we think the material is taught in the wrong way. So I'm kind of flipping the material on its head so that I'm starting with the end material and ending with the beginning material in some way. And the reason for that is that it's much more intuitive, and it starts with the hard material and ends on the easy material instead of starting easy and ending hard, which I think that would be most loved by students. So those are the main reasons why I did it that way. Any questions on this page? Okay, so let's get into material, unless there are other questions. Yeah.
Sorry, this was answered, but when did the link go live for choosing which one you want?
It's already there. So this link right there, that link is already live. So if I go to that, you have to be signed into your ASU email in order, because it'll give me your ASU Red ID, and then I can link it to Blackboard, that sort of thing. Yeah.
Homework 1 is due July 4th?
Yes.
July 4th at midnight?
Yes. All due dates are midnight to keep things super easy. Yes. Oh, when is quiz 1 due? Monday. So when are quizzes coming out? Every lecture or every other lecture? Every lecture. Okay. So when's the second quiz come out? Monday, and it's due? Good. So hopefully you're on track with that. On top of that, the quizzes should be super easy in terms of that there are only 5 questions, and they should be entirely based on the lecture material. So those should be just as a self-check to make sure you're following along. Any other questions before we actually get into material? Yeah.
So wondering, are the problem sets that you give, are they representative of what the exam will be like?
Most likely. Yeah.
Is there anything specifically to do with class or that makes you not?
Other than exams, no. So because we have people traveling everywhere, I think it'll just be best to handle everything online. Yeah.
So there's no attendance?
No. But I can tell because I have the roster with your photos in it. I know who's here and who isn't. So, yeah. Any other questions? Oh, one more thing. So the lecture, how the lectures go is an hour lecture, 5-minute break, and an hour lecture, because I don't think anyone wants to listen to me for 2 hours straight. Heck, I don't even want to hear myself talk for 2 hours straight. So at 6:25, we're going to take 5-minute break, 6:30, come back. And then right after that, obviously, office hours. Other questions? Before we get into the awesome material. Any questions? Okay, so how do you even begin this material? So why is your degree called computer science and not computer programming? Or something else? What does science mean? It's a theory of or study of, right? So it's the theory of computers or what? Computation. So being able to compute something. And so what we want to be able to do in this class is study computing. So basically everything that you've seen in your past classes is based off of the theory that's built up in this one. So what we want to do is to study the theory of computing. And by the way, I have the lecture notes with me, so if you're following along in the PDFs, I do have them here, so I do have that in mind, so no worries about that. So when did the theory of computation or computing actually start? So if you, once you get to this class, you'll start to think that this class is more applied math than what you are used to as computer programming. So you can think, well, applied math goes back forever. So when did actually computation actually start? So some folks in the 1930s, one of them is Alan Turing, so 1930s, as well as Alonzo Church, both in 1930s, as well as other people later and before them. They were trying to understand what numbers are what are called computable. So the question that they were trying to answer was, what numbers are computable? So for some definition of computable, what numbers are computable? So what computable means in this sense is that it's some finite time algorithm, although that's redundant, I guess, to given n, an integer, output the first n digits of that number. So of course every integer under this definition is computable because I can just output the integer itself. So any finite length integer can always be computed because I can just store all finitely many digits and then just output them when necessary. So the issue may happen when the expansion of the number is infinite. So either rational or irrational numbers. So it turns out rational numbers are computable because their representation repeats. But irrational numbers, in fact, most of them are not computable, which is what they have found. So in fact, most reals are not computable. Some of them are, like pi and e, and some of the more famous numbers are computable because you can have an algorithm that outputs the first n digits. It may take a long time, but it turns out it is possible to do. But there are some numbers that do exist that are not computable at all. That you can't, for all n, output the first n digits in a finite amount of time. Okay? So what we are trying to do here is basically the same thing, but in a more computable type of sense. So what we want to know is what problems are solvable. So solvable in this sense means that we can solve the problem using an algorithm, some finite time process. Okay? So what problems are actually solvable? And it turns out these two questions are exactly the same question. And what we'll find is that the vast majority of problems that we would like to solve are not computable or not solvable by any algorithm. It doesn't matter whether you have every single core at the NSA. It doesn't matter whether you have harnessed the computational power of every computer ever to exist and ever will exist since the Big Bang. There are some problems you cannot possibly solve in any finite amount of time, and we'll prove it about a week from now. So what we want to know is, what problems are solvable and which ones are not. And so you may think, well, there are some problems, pretty much every single problem I've ever seen so far is solvable. I have it on my computer and it runs in 1/10 of a second. I perform breadth first search of this really small graph and it finds an answer very quickly. So let me tell you that on my desktop machine at home, about a year ago, I had a program that ran for 6 consecutive weeks. Not minutes, weeks. How do you know if it's going to stop? Well, in fact, I designed the program, and I actually know for sure it would never stop. But if you're just sitting there looking at a program run, how do you know it's going to stop? Who's written in an infinite loop before in some program? If you haven't raised your hand, you are lying. So literally everyone who's programmed has made an infinite loop, either by accident or on purpose. And so you may think, well, you have this problem on your computer, Ryan, and some people may have some problem that they don't know whether their program halts either. So maybe we can be entrepreneurial here. What we're going to do is we're going to make some program. So for the entrepreneurial in the class, my awful spelling of entrepreneurial. So what you could do is, so we can make a program that tells whether or not an arbitrary program as input will terminate. So I have several examples of programs that we don't know stop in the lecture notes. And so if we could do this, then we could just feed these programs or mine at home or whatever program you come up with. And if we can do this, then we can either solve some mathematical conjectures or do research for me or something else, and we could improve the world substantially. We can sell this to Google and we'll be billions of dollars richer. So do you think we can actually do this? No. So in fact, this is impossible. So what if you've looked on the internet, this is actually what is called the halting problem. So I give you a program as input, and you tell me whether it stops. And in fact, there's no algorithm to determine that. All right. So let's see. So what we're going to claim is that no algorithm at all can solve this question or any question related to it. So what we want to figure out is, well, we're trying to say something about literally every single algorithm that could exist, has existed, or ever will exist. So how do we can't just go through algorithms and say, this one doesn't work, this one doesn't work, this one doesn't work. How many algorithms are possible? Infinitely many. Is that going to take a long time? It's going to take an infinitely long time. So we need to be able to develop some machinery for talking about some way of expressing all algorithms, or have a formal way of saying this is a computational problem of some kind, or this is an algorithm in a formal way. So what we're going to do is we're going to encode problems as strings in a language. So who does not know what a language is? So everyone's seen language. All right. So the idea here is we're going to encode problems as strings in a language. So this kind of bugs me a little bit, but can anyone tell me what a language is? What's a language? English. No. Set of strings, yeah. So this is a set of strings. Are strings finite or infinite? Strings finite or infinite?
Fine.
Finite. Can languages be infinite? Yeah, what about the set of all binary strings? How many of those are there? Infinitely many. So that's one example. So the way that we want to encode problems is in the following way. So if we have an instance x to a problem, we're going to encode as this thing, which is angle brackets with the thing in the middle. So this is what is called an encoding. And all that really means is we're going to transform this into a string representation. That's all it really is. So for example, if we just have a normal string, so if x equals that as a string, then the encoding of x would just be the string itself. That's one way to encode it. Of course, there are many other ways we may encode it. We may put delimiter signs, we may do something else, but there are many ways we can encode something. So in the lecture notes, I have, what if we try to encode a graph? So what could be a graph representation or an encoding that we could use? So we're transforming the graph into a string that we could recover. So if I give you this string, you can figure out exactly which graph I'm talking about. What's one way we can do that? So one way we can do it is list vertices, then delimiter, then edges. Okay, so for example, we may have vertex v1, v2, v3. Let's say there are n of them. And then, so this delimiter at the beginning just denotes, hey, this is where the encoding starts, and then the vertices will follow right after it. And then the second delimiter is to say, the vertices list ended, now come the edges. So then we may have E1, edge 1, E2, and then EM. And then the last delimiter is to denote, hey, the edge list is done. So all we're doing, it seems very vague, but all we're doing is we're transforming a problem instance into a string representation. That's all we're doing. So it's basically a way of providing the input to a computer, because a computer can understand strings or inputs as strings, but it can't represent, hey, I drew you this graph. Can the program figure that out? Probably not. But it can figure out, hey, I have this list of vertices, then list of edges. Now I know what graph it is. Okay? So what a computational problem is, so I have a language L, and it has encoded inputs as X. So the reason we encode here is that we want to be able to put this into a set so that we can start doing set things with it. So we're saying that it's a set of encodings X where X has some property. Maybe for graphs, what could be some property of a graph? It's a tree. Another one might be it's connected or has more than 1,000 vertices, that sort of thing. So all graphs that behave according to some property. Any questions about that? Am I going too fast or? Yeah. What's that? Okay. So if you have any questions at all, feel free to stop me, because I know the material so well, and if no one says anything, I tend to go faster, so which could be hazardous. Yeah.
So just getting the string
Yeah, so it's for all x's that have some property, I'm going to look at the encoded version and put those into the set. So the one I have in the notes is this BIP thing, which is all graphs, G, where G is bipartite. It's actually very closely to the tree example that was given here. What is bipartite? Okay.
This is one, we can divide it into two sets where one set of nodes will never have an edge between them, while it will have an edge on the other.
Right. So bipartite means that we have a list of vertices, actually two lists of vertices, where edges will go in between the two lists, but no edges between inside each of the two sides. So you can basically say the edges only cross between these vertices. And so the BIP problem then is I give you an arbitrary graph and I want you to determine whether or not that graph belongs in BIP. In other words, the graph is bipartite. Okay? Another one I have here is primes. So if I have, actually I'll just write it here. By the way, I have no idea why the language names are always capitalized. That's just the convention. It's not like I'm shouting at you or anything. So the primes language is a set of strings x. I'll make that easier to see. Where x is a prime number. So what would the corresponding computational problem to primes be? So what are you given as input? A number encoded as a string. What do you want to determine? If it's a prime, or more formally, whether that encoded input x belongs to primes. Yeah, whether it's in this language. It intuitively means the same thing, but formally what we mean is that this encoded input is in this language, primes. Okay? Any questions about that? Because we're going to be talking about computational problems quite a bit. So we're going to have a language, and we want to determine whether an input belongs to that language or not. And basically the entire class is based on that. We're going to be given some input, and we want to figure out, okay, can I figure out whether that input belongs to that language or not? In some cases, yes. Most of the cases, no. And more importantly, what types of resources do you need to be able to figure out whether that input is in that language or not? So if I say restrict the amount of time you are allowed to use in your computer, does that restrict what types of computational problems you can do with that resource restriction? Okay, does that make sense? Okay. Cool. So just a few other things about languages before we move on. So we're going to let sigma be a finite set. It's sometimes called an alphabet, and most of the time we'll call it an alphabet here. But it's just the same thing as a finite set. So there are some operations on sets that we can do in terms of languages in order to build up to other languages or get to smaller languages or talk about some strings and that sort of thing. So we're going to denote epsilon to be the empty string. So it's the only string with exactly 0 characters in it. Okay? Let's see. We're going to denote this symbol, it's not phi, but it looks like phi. to be the empty set or empty language. So the way of saying this is that it's the only language with 0 strings in it. Are these two the same thing? Empty string and empty language? Can a language be equal to a string? No, because a set can't be equal to a string. Yeah. So these two are not the same. So can anyone tell me what concatenation is? Yeah, you take 2 strings or whatever and you put them together. So it means the same thing here. So concatenation of 2 strings W and X is WX. And all it means is you take the characters of W and then you stick onto the end the characters of X. In other words, you just put them together. You should be used to that by now. What is W concatenated with the empty string? W, yeah, because you guys are good. Yeah, because I'm putting 0 characters on. What if I put an empty string on the beginning? Yeah, same thing. What if I had 10 trillion empty strings on the front? Again, same thing. Is that clear? Okay. So for 2 languages, the concatenation of languages A and B is written A with B right after it to be just, you take a string out of A and you concatenate it with any string in B. So I'll just write it down first. So you just take any old string you want in A and you take any old string you want in B and you put them together to make and you put that string into this set AB. Okay? For any language A, what is A concatenated with the empty language? Ooh, be careful. How many strings are in the empty set? 0. So I'm concatenating any string in A with nothing. So it's the empty set. Okay? So it's just these corner cases you need to be a little wary about, but it's just applying the definition.
So you're selecting an arbitrary string in the language to concatenate another arbitrary string?
Yeah, so an arbitrary string in A with an arbitrary string in B. Yeah. Any questions about that?
So the order matters in BA.
Yeah, right. So is AB equal to BA in the general case? No, because in fact, if A and B are different languages, then they won't be equal. The AB is not equal to BA is what I mean. Okay, so this one will warp your head a little bit. So let L be a language, and we're going to define L to the 0 means the set which only contains the empty string. Question: is this equal to the empty set? The string, the language with the string, empty string inside it. No. How can you tell? They don't even have the same cardinality, so there's no way they could be equal. So in fact, these are not equal. Okay. So the superscript here means we're going to apply concatenation to L itself the superscript number of times. So 0 times means you pick 0 strings out of L and you concatenate them all together. Well, you just get the empty string out of that. But if I pick I strings out of L, that just means take 1 string out of L and then I minus 1 more. So we're going to have L with I minus 1 more. So so one way you can look at this is LL equals L squared. So the 2 on top just means I take a string out of L twice and I concatenate them together. It's just concatenation, but done a number of times. And we're going to write L star to be the union over all I at least 0 of L to the I. So this is sometimes called clean star or cleany star, if you want to be annoying. So what this means is if you have a string in L star, then that just means taking some string out of L, but not a single string. You take some number of times, you take any old string you want out of L, and you concatenate them all together at the very end. Okay, so for any number of times you want I, you will take I strings out of L, maybe the same, and you concatenate them all together, put it in L star. So as an example, what is 01, which is a language, star? So take any number of strings inside this language, which is only 0 or only 1, and you concatenate them all together, as many as you want. So what is this? Yeah, any combination of 0, 1, or more informally? Binary strings, yeah. So this is binary strings. So I'm going to add another Piazza question here. It's not in the notes. What are empty set star and the L0 we had earlier? Just empty string star. And then we can discuss on Piazza what those two are. And it's actually quite interesting. Any questions so far? So all that really is to get some background here. There's a background PDF on the website. If you don't understand some of this here, there's a little bit of a background there that you could look at if you need a refresher. But any questions? Okay, let's go to Turing machines. So back in the 1930s, I mentioned these two people, Alan Turing and Alonzo Church, and of course other people. So they were talking about things that are computable, right? They were talking about these number things and what numbers are computable, which ones are not. So, of course, they didn't know what a computer was as we know them today, right? Because it took until the 1960s and 70s and whatnot to build up to what we have here with von Neumann architecture and whatnot. But the word computer was actually used back then. And not in the number sense, as I mentioned. So does anyone know why computer was a word used back then? And what was it used for? What's that?
People do computations by hand.
Yeah, it actually was a position that you could apply for to be a computer. Kind of interesting, right? So what happened back then? So what is a computer? Reference to Apple commercial. So what was a computer back then? So we had this person, so I failed art, but we have this person who's working at a desk, and what happened on his desk were 2 stacks of paper, perhaps more, but let's just stick with 2 stacks of paper for now. Maybe let's make this one small. And what the person was supposed to do was, on one of the stacks, the person was supposed to look on the piece of paper, and it had some information on it, some computation that was hand done by that person. And depending on what was on the piece of paper, he either moved that paper to the next sheet, to the other stack, and then started working on the sheet right under it, Or what would happen is the person would write on the piece of paper and possibly move it to the other stack, or any one of those combinations and take a paper from the other stack and put it on the first stack. Okay? So it's basically, we're going to be working on these pieces of paper and then work on the next piece of paper. So that was the notion of computer back then. But of course, the notion of computer is completely different now, right? It seems completely different, but in fact, they do the exact same thing, as we'll see in maybe a week. But we're going to analyze a machine model that behaves like that model that Turing was thinking of way back in the 1930s. So what would happen is we're going to think of a model for this exact situation. So the model that we're going to talk about are called Turing machines. So what we're going to think about here is Turing machines are going to solve computational problems. So there's some language that they want to be able to solve, and they're going to have some work area that they can work on and maybe do the same things that the computer person could do. So of course, in the computational problem, what are you given? Some encoded input of some kind, written somewhere. And then what the Turing machine is going to do is going to do some simulation of some kind. And this computer person actually did not have any choice as to what to do. What that person was to do was prescribed right from the beginning. So there's no choice whatsoever. So what we're going to be working on is what's called a tape. And it's an infinite tape, infinite one-way tape for now. And just like the piece of paper analogy, we're going to provide the input on this tape. So maybe we'll have hello written on here. So hello is the encoded version of some computational problem. And just like the person, we got to start somewhere on the tape and then do some computation with that. So the Turing machine, what it's going to do is it's going to have what is called a tape head. A tape head that's going to be positioned at the first character on the tape. So in this case, what is it pointing at? H, good. And what the tape head is going to do is either it can move right or it can move left. So just like the person, that person could either take a piece of paper from the other stack or move on to the next piece of paper in the current stack. But instead of thinking of stacks, we're going to think of tapes here, but it's analogous. So in fact, the tape head is going to move right and left. And what we're going to do is we're going to have a state-based finite control on the back end. So the tape head is going to communicate with some finite control. And so now you're thinking, wow, Ryan's lost his mind already, right? So does this seem completely off the wall crazy? I won't be mad. So what is the motivation behind this? Well, there's actually two. The finite control is because the set of rules that the computer person has to follow is a finite list. It may be a long list, it may be intractable to look at the list, but it's a finite list. But another reason is if these Turing machines are in fact the same computational model as we know them today, then the amount of memory we have in our computers is a finite amount, right? And so that's where the finite control idea comes from. So yet another one is if you have a program and it's doing some computation, well, what's it going to do? It's going to fetch some instruction, and then what's going to happen? Well, a lot of things can happen, but could the memory layout change of your computer? Yeah, it could change. Could it stay the same? Yeah. But how many possibilities are there for your computer to be in, for your memory? Well, let's see. If there are n bits, let's say, in the computer, how many possibilities for the contents of that memory could there be? 2 to the n. Possible. So what we're going to call each one of those is a state of the computer or the machine. Well, and now you're saying, well, okay, well, my computer has X gigabytes of storage and 2 to the n is extremely large. Is it infinite? Or is it a finite number? So that's where the finite control idea comes in. So we're going to have some finite control that's going to control the tape head as it's moving right to left, right and left. And I said that this tape was infinite, right? Well, the input is a string. Are strings finite or infinite? Finite. Oh, wait. What happens after the input? There must be something there. The tape is infinite. So we have this special character, which we call a blank. So it looks like a square with the top cut out of it. That's actually not what it is, but it's a special blank character to denote, hey, this is where the input is at the very beginning, and the rest of the tape is a blank character. Okay? What else do I need to say? Okay, so just to recap, we have this finite control, and it's going to look at what particular state the machine is in, look at what symbol it's reading on the tape, and then based on this finite control, figure out, okay, here's the state I'm going to go to, what memory layout's going to change. Am I going to move left or right? And should I write a different character where I was before? So if I'm looking at this hello input right here, maybe the thing to do is write an X right where the H is, and then move right. So after that happens, what will the tape contents look like? If I write an X and move right, move the tape head right. What will the tape contents be? X-E-L-L-O, yeah. But is the tape head still pointed there at the first character? Where is it pointed now? At the E. Okay, that's good. Well, let's see. Well, now I just destroyed part of the input. And there's no history as to what it was before. I completely erased what was on the tape, and I put an X where the H was. How do I know when to stop? Right? So since I destroyed the input, I don't know what the input is anymore. So I can't really decide this anymore. So we'll need a special way to say, yes, this input is in this language for the computational problem to stop the machine, because if we just let this run, it could run forever. And another way to say, this machine is going to stop, but it's not in the language of the computational problem. So as an example, maybe the graph I'm given is not bipartite, and then I find a way to say, yeah, the graph is not actually bipartite, here's the reason, and then stop the machine there. Or if it's a prime, I found a divisor of this integer, therefore it's not in primes. So that sort of thing, to tell when the machine is going to stop. Okay? Any questions before we move on to the actual formal statement? Okay, so so how are we gonna do this? So I'm actually not gonna move on to the formal statement. We're going to make a Turing machine first and then talk about the formal model, because it's much easier to derive the formal model when we actually have a picture of a Turing machine to start with. So the one I have in the notes is this language, 0 to the n, $, 0 to the n, where n is at least 0. What is this 0 to the n thingy? Yeah, it denotes concatenation. So here, because 0 is a string, 0 to the n means n repetitions of the string, which in this case is 0. So just to reiterate, this is 0 repeated n times. So is the input going to be of the form n zeros, $ n zeros? Is it always going to be of that form? No, it may be like $1 trillion in a row, right? It may be of that form. What am I supposed to do here? I'm given this input, and what am I supposed to do? Check if it's in L, okay? Using this Turing machine thing. So actually, before we move on, I think it'd be a good idea to have a 5-minute break now, and then we'll come back to this example.